Okay, now we can expand more on the isovolumetric, isobaric, and isothermal processes. In the following chapters, I'll go over the adiabatic expansion. That one is a little bit different. Adiabatic means no heat exchange, okay? But we'll talk about the isos first. The isovolumetric is constant volume, volumetric. Sometimes it's called isovolumic for short, constant volume. So that means the piston is bolted into place, the gas can't do work, and you're not doing work on the gas. The volume is not changing, right? Well, since negative Q out of gas is the same as Q into gas, we can say change in internal energy of gas is equal to Q into gas. So that's what we saw in the last theory section where I put it in the ice bucket water. The change in internal energy was negative 60 joules of heat went out. And then the change in internal energy was negative 60, and then the volume didn't change, right? The PV diagram for this, we can make PV diagrams, right? So if the initial pressure P1 is here, and the initial volume V1 is here, depending on if you're putting it in an ice bucket water, right, and bolting the piston, then the pressure is going to drop, right? Remember in the example I did, it went from P1 to from 1 atmosphere to half an atmosphere, right? So it dropped from P1 to half P1. So it went from here to here, downwards direction, right? If instead we put it in a hot boiling water, right, what would happen? If the water was hotter than the gas and we bolted the piston, then the pressure would go up, the volume would also not change, and it can go up to 2P1 or 3P1. It all depends on what the temperature of that hot water container is. So this one could also drop depending on what the temperature of the container is that you put it on, right? So it could drop down to half P, 3/4 P, or 1/4 P, okay? So basically the PV diagram of the isovolumetric just goes this way, up and down, and since the gas does no work, the work is the area under the pressure and volume graph, right? Work is equal to, remember it's integral of f dx, right? In physics 1, we write it as integral of f dx, but in thermodynamics, we divide f by a, and we multiply this by a, and we write the work as integral p dv, right? Since the pressure is not going sideways, there is no area under the graph of p versus v, and therefore the gas does no work, and you don't do any work on the gas, right? So the work in this case is just 0, okay? So now let's talk about isobaric, and then V1, and then the pressure goes like this, stays the same, and then V2. So what's the work done by a gas in a constant pressure? Well, if it's going this way, then the work done by the gas is going to equal P delta V, right? So it's going to be P V2 minus V1, right? In the case of the ice water mixture, when I put it in the ice bucket water, in one of the cases, right, the volume went down to 2/3 of its value. Remember when V final was 2/3 of V initial, right? And then we saw that the pressure stayed the same. So in that case, it went the other way. It started at V initial, and it went all the way to 2/3 V initial. 2/3 V initial. So it went this way. This is P initial, right? And then the work by the gas is what? P delta V, right? So it's going to be P, and then we can say here V initial minus 2/3 V initial. So we can say this is V initial. So then the work on the gas is going to equal P V initial minus 2/3 V initial is going to be 1/3 V initial. So PV over 3, right? So when I do, later on when I do problems, I'll do these with all numbers and stuff like that, right? Here I was calling delta V the absolute value of the change in volume, right? The absolute value of the change in volume, so that this is positive and this is negative because I know that the work by the gas is negative, okay? And then here this is P delta V, and again this is the absolute value of the change in volume, so I'm doing the initial volume minus the final volume, because I know when you're going this way, the gas is doing negative work, and the work is being done on the gas, right? Okay, how about isothermal? Isothermal means the temperature is staying constant. So in this case, the change in internal energy is 0, and the work on the gas is the Q out of gas, right? So again, if you are doing work on the gas, right, heat is going to be escaping. So it depends on what the PV diagram is. So what does the PV diagram of this one look like? V1, P1. If the volume is expanding, then the gas is doing work, right? So we can say work by gas is Q into gas. So if I take this, if I take the negative of this, it's going to be Q into gas. If I take the negative of this, it's going to be work by gas. So V1, P1, V2, P2, and then the graph of this looks like this. It's an isothermal graph. Now why does it look like that? It has to do with the ideal gas law, right? PV equals nRT. If the temperature is constant, the pressure and the volume vary like what? P equals constant over V, right? So that means the PV diagram is going to be like y of x equals 1 over x. So it's going to drop like that. So in this case, what would be the work done by the gas? The area under this, right? So it's going to equal what? Work by gas. Well, you can't just say P delta V in this case, right? Because the pressure is not the same. It's not like a horizontal line. The pressure is dropping like 1 over V, right? 1 over V. So you're gonna have to say P dV and then integrate that. So work by gas, and then what's the pressure? It's the constant over the volume dV, V1, V2, right? And then so work by gas is going to equal what? Whatever the constant is, what's the integral of dV over V? Well, that's ln of V, right? So ln of V2 over V1. And then what is the constant? The constant is nRT. The number of moles times the gas constant times the temperature, but the temperature is constant, right? So then you can say here nRT ln of V2 over V1, okay? That's going to be the work done by the gas. If the volume is increasing, the gas is going to do work, and then the heat is coming into the gas, right? We can write it this way. Q into gas, right? If you're going the other way, if you're going backwards, this way, that means the gas is being compressed, right? And then heat is going to escape the gas. So then the heat is going this way, and then we write with arrows like this, Q out of gas. Okay? So we can summarize all three of these processes just on one board. We can say, so just on one board you can summarize all three. Isovolumic, 0, Q into gas, delta E of gas. Isobaric, Q into gas is delta E of gas plus work by gas. Work by gas is P, V2 minus V1. Isothermal delta E is 0. Q into gas is equal to work by gas, right? And then the work by gas is the nRT ln V2 over V1, okay? Following chapters, you'll see more detailed coverage of this material. I'll go into adiabatic processes and we'll do more complex examples of this, okay? Thank you very much.